whatever we have done till now, before we shift gears and go through a real aperture camera, I wanted to kind of open your eyes to some of these things, what are called research challenges. So if you think that, right, in a camera motion, okay, right, it's all kind of done stuff. All right, right. So, okay, it looks like some issues when there is a depth change, some issues here and there, but then right beyond that, probably is this all done? If you ask that question, the answer is no, it's wide open. Okay, it's wide open for those of you who are interested, right? Unfortunately, the world has come to a stage now that whenever I see anybody on so it's like when you walk on the corridor, you just find everybody, right? You're an important man if you have a cell phone. You're not an important man if you don't have a cell phone, right? Just see that every other student or every other person is so immersed, I don't know, right, WhatsApp, right? So it's like that, right? So I felt that maybe out of this 40 odd people, at least there may be 1 or 2 people who are not so probably that on to cell phones, and maybe right, they also think that there is a world outside of the cell phone, right? So, I'm saying it's a fact, okay? When I see around, that's what I see. So the idea is that, right, if you, so what I thought is I'll just walk through some of these research challenges. Right? This is not for everybody, right? This is just to open your mind to things, okay, that are out there, that are actually interesting, many of them are still unsolved. And for those of you who are kind of, research oriented, you should also know that, there is one part which is like, which is like easy to follow and, which is done stuff. And then the other part, right, where you if you want to, right, escalate the bar, if you want to raise the bar and say, okay, no, if I raise the bar, what else can happen, right? Then this will kind of give you a window for that. Okay, so right, prior to so all this, so I'll tell you, right, a few of these things. What is that? Okay, right, so the first one, right, that I just wanted to point out to you is that, and these are all from my lab only, okay, all these images are our own, so it's okay, so we can share with all of you. So here, right, this is an aerial image, and if you really notice, right, okay, so what you want to do is you want to align the two images. So this is aerial, so you can sort of assume that probably the world is flat, right? Even though we know that world is really not flat, there is of course variations, and also there are cars and so on, trucks and so on, okay, and these are real images, okay, this is not something that I have synthesized or something, these are actually real, and it's called a Virat. Virat is this particular data set, so it's available for everybody. So you see these two images now, okay, there's one on the left and there's one on the right, and you see that there is a change that has happened, right, between the two. What changes do you see, right, when you see with your eyes, right, what do you kind of notice? You notice that there is a vehicle, right? There is a new vehicle that has come in, right? Which is this truck, right? Some truck has come in here. Anything else that you notice? Okay, right? There is some kind of motion. The camera has undergone, so it's not the same viewpoint. It's not like you're looking at it exactly from the same point. What else? Sorry, car is moving around. Yeah, agreed. Okay, so sorry. Yeah, that car I already indicated, right? That's a new object in the scene. Then we are saying that there is some camera motion, right, between the two images. And then what else? Right. So what she's saying is the first one is slightly blurred. Right. Again, sometimes, right, if you see here, it'll be much more. It's easy to kind of perceive. Whereas when you're going to blow it up on this thing, unless you have a projector that can show it all, right, you may not be able to appreciate. But for those of you with subtle eyes, right, you will kind of notice that right, there is some blur in the first one. Okay, so the whole point is, right, so if you try to now compare these two images, so if you go back and look at the SIFT thing, right, which I kind of talked about yesterday, that you can still use, okay, fortunately, SIFT features still work even if there is some blur. The sense that what it will mean is, and yesterday, by the way, somebody asked me later a question outside the class, as to how, so what is this SIFT kind of, do you give it points? No, you don't give any points, right? It's like saying that you show this image, right? And then its job is to find out all such interesting points, whatever it thinks are interesting. Okay, it'll automatically pick. We don't go around and tell, right, look at that region or this region and so on. Right? So it'll just pick. For example, right, it might just pick that, it may just look at this car, the edge of the car or something, and it might think that, okay, there is something interesting there, which it can then also relate here. So when I say a correspondence, what it will do is it will tell that there is an interesting feature here, and that feature occurs there in the other image, inside some other location. And similarly, something here is something there, maybe something here it might pick, maybe there is something out there, it might pick there, pick at the other. Sometimes it can also go wrong. Okay, that is the reason why I said that we have to use some kind of an outlier handling, right? Otherwise we could go wrong. Now, so in this case, what I'm saying is, even if you use shift features, and suppose, right, you are able to align the two, right? Once you get your shift, that means you can align the two images. But then after you align them, if you slap them, right, one on another, they will be reasonably aligned now, because of the fact that you've already found what is that homography, right? That maps the two. But if you try to subtract the intensities, thinking that will tell me that will probably show up only this object, it won't, because of the fact that the first guy has some kind of a blur in it. Okay, now why it might have happened is because there was something that was just moving. You had an aircraft which was moving, and it kind of captured an image. So right. So when you actually move, you integrate scene points. If you're still, right, you can imagine that there's only one scene point that is hitting a pixel, right? As long as nobody moves, there is only that photon only coming from that scene point only. But if we start to move, right, then it means that when it means that the same pixel will also get from some other fellow, from some other neighboring fellow. So all these will get integrated, and then you start seeing blurring effects, right? So similar. So if you just slap one on top of the other and then say that I can subtract now, and I'll try to be, and then I can get the changes detected, then you will go wrong, because it will also indicate changes in many places, simply because the intensities don't match. Okay, so which is the reason. What is important here is that one of the key challenges is that when there is blurring, especially for aerial images, it's a problem. Whenever you're moving, you're capturing, and so on, you can't simply assume right that these images images will be sharp and so on. And therefore, you can do it in different ways. The goal is not to really talk to you about what this, how you solve this and so on. I just wanted to show you that there is so much more to all of this than, right, what we actually do in the class. What we do in the class is simply to lay the foundation, right? Just to know that, okay, what lies out there, what simple things can you do. But those of you, right, who want to go for higher studies, or those of you who are already in higher studies, who are already PhD students here, or MS students here, or the dual degree, or the BTech guys who are going for higher studies, right? So for you people, it is important to know that there is much more to it than what can see meets the eye in the class, right? So which is why I thought I'll actually show you these things. These are fairly interesting, right? So here, of course, you can see that this dark regions come because we have done some alignment. And then what you need to do is, one of the ways is that you should actually compensate the intensities now. Either you can make the other guy sharp, in the sense that you can sharpen this and then match, or you can actually blur this guy up to the same level as this and then match. One is called re-blurring, another is called de-blurring. So de-blurring means you remove the blur so that right, both are sharp and you match them, or you re-blur, which means that one guy which is already sharp, you get a blur on top of that. You apply some blur so that it looks similar to the other one. Again, right, what should be the amount of blur? I mean, is the blur a constant all over the image? What if the blur is changing? All those will still, right? I can talk on this one problem for an hour. Okay, so each one is very involved, but I just wanted you to know that, right, there is something like that. So now if you do that kind of illumination compensation, and then if you do a detection, then you change, then you, of course, rightly you find that, okay, there's only one object there. That is actually the change between the two. The rest of it is all, right, artificially induced because of some blur, because of whatever else, right, camera motion and all that. So ideally, you should be only detecting that object. Next is this. What do you think this is? This is inside our campus, okay? I hope you recognize your own campus. Okay, now this is called, this is a pan photography. Pan photography is a name for this. Okay, this is one of my PhD students' works. Pan photography, right? If you go and check what is pan photography, what it says is that, let us say that you are inside our campus. We have very nice examples inside our own IIT Madras. So let's say you see a deer that is fleeting, okay, and then you take your camera, and what would you like to do? Ideally, you would like to move the camera in sync with the deer, so that in all your images, the deer looks focused. I mean, as long as imagine that if you can move in a manner that you are completely in sync with the deer as it moves, you cannot see any blur, no, because you are actually moving at the same rate as the deer. So all these relative points are all kind of locked, correct? So you can't see any blur because there is no relative motion between the camera and the deer. Okay, now if you are an expert photographer, is there anybody here who's an avid photographer? It's okay. You can raise your hand. Anybody that has heard about pan photography? So what this actually means is that, so if you are an expert photographer, you can actually you can pan in a manner that this object of interest stays locked as it moves. Okay, so ideally, what do you think? Suppose I showed you a picture. Suppose I showed you one shot of that. what would you see? What would you show to a person? How would that image look like? Suppose somebody did that, he's an expert, right? Let's say this boy here is an expert in photography, right? He does that. What will the image look like? There is a deer in front of Himalaya mess. Huh? So you will see that the deer is focused, but what happens to the background? The background will be blurred by how much? By the same motion as that of the camera, or the actual deer, whatever the deer motion was, because your camera motion is exactly in sync with the deer, right? So that is how a pan photograph is supposed to look like. Right? But then if you and I take a camera today, and then if you try doing that, right, you won't be able to do it. Okay, it's not possible for every one of us to be able to be so exact. So what we do is, we simply take, but it can so happen that, right, we kind of moved probably a little too slowly, or we moved a little too fast and so on. Right, all that can happen. So the idea is that if you were to capture a bunch of frames like that, now what will typically happen is, you can also have these two not being at the same depth. The sense that you can have the trees far behind and there's a deer right too much in front, in which case right, you have to kind of worry about the fact that the world is no longer a single plane. If you are fortunate, then maybe the deer is far away and therefore the whole world looks planar, and then you move and there is a foreground object that's moving, right? So one of the things that is actually done is even to kind of locate where this moving object is. So what will typically happen is, you compute these shift features, okay, across the frames, and then you match the shift features across what is a moving object versus where you have a background, and then you segregate the two, and then you kind of realign this moving object such that it stays in the same place. See, for example, the second video, this is playing, right? What do you see between these two? There is a kind of subtle difference. Do you notice that? The background almost looks stationary, right? So it just looks like only this guy is moving, and then the background is completely stationary, right? So what you get as input video is this, and then eventually, right, what you would like to show is this, where this guy is completely in focus, and then the camera motion has been imbibed by the background. That is how, if you are an expert photographer, right, this is what would have happened. Okay, this is how you would have caught that image. Okay, and of course, and then you can complicate this problem. You can say, what if the foreground is also blurred? Then what do you do, and so on. Let's not get get into all that. But the idea is that something using shift features, something based upon this homography idea, right, wherein right, we are kind of realigning and so on. I just wanted to show you as an example of something that you have learned, something that you can apply. Okay. Of course, with some kind of background, right, about this particular problem. But I'm just trying to say that even with simple things that you have learned till now, you can do things that are interesting. Look at this, right? This is again a leopard or something, right? Now, by the way, so this is a rolling shutter. I think I showed you, right, maybe in the first class itself, I showed you a rolling shutter example. The rolling shutter is an extreme case, right, in the sense that, right now, okay, we are talking about one homography, right, that matches, okay, two images. Now an extension of, right, what you have already learned is when, let's say, right now what you are assuming is that all the sensors, right, are kind of opening at the same time, or when the camera gets exposed, right, all the sensors get exposed, right, and therefore if there is a camera motion, that is global. So every sensor is experiencing the same motion. Now what happens in a rolling shutter camera, which is what incidentally all of your cell phones have, is that, right, you don't really expose all the sensors at the same time. It's called a rolling shutter because it's like saying that if you had a shutter, right, that would open slowly. It's a rolling shutter, it's like a car shed where you open the shutter. So what happens, initially some things are exposed, then some things and so on, right? So what will really happen is as the scene points keep coming in, right, the let's say if you think of the first row as being exposed first, then after some time you expose the second row, after some time you expose the third row, and so on, then what will happen is, as long as there is no motion, it doesn't matter. Then the problem is exactly identical to what you had. At the end of it, if there was no motion, then of course you will get a nice image. But then what can happen is your camera, right, could have actually moved, okay, during the time that the that this rows are being exposed. So what will happen is the first row, the motion that it saw, right? I mean, imagine that, right? You are opening it for a certain amount of time. The exposure time is the same for all the rows. Okay, but what will happen is when you kind of delay it and then open this next row, you will see that there is some motion that they both see, but there is some motion that this guy never saw, which the first row saw, and there is some motion that this guy sees later that the first row never saw, right? So what will happen is, so when you do like this, what can happen is, right, a straight line, which ideally should have come as a straight line, can now start to bend or can start to look skewed and all that, right? Because it is all completely dependent upon how you move the camera, right? It is all a function of what you do with the camera. So what will happen is, right, so you actually end up with images like this. This is our own ESB corridor, right? So you see this bend here. Now ideally what you need to do is, if you want to bring it all back correctly, then you're almost saying that, there is a continuous change in motion as you walk through the rows, right? And you need to know what is that motion on a kind of row to row basis in order to be able to rewarp and be able to get back what should be a clean image. I mean, do you see the point? I mean, right, on the one hand, you had just one homography, it is the simplest case. Now, ideally here you could have, if you have n number of rows, you could have n number of such homographies to solve for. That's not the way we normally do it, because people do some interpolation to make the problem simpler. They'll pick some key rows for which they'll find the motion, they'll find the homographies, and then the rest of it they'll simply interpolate across the rows, because typically camera motion is not very arbitrary, it's not very abrupt. So you can assume that there is some smoothness in the motion, therefore you kind of interpolate the camera motion, and that's how you know the homography that you need, and then right, you can still align and then get back something like so you see this guy, so this would be a corrected image. And again, how you do the correction, right, whether there is a lot to this, it's not so straightforward as I am telling, okay, but and then see the other building, right, it almost looks like it will slant and fall off any time, right? But that is because of the way you have captured. And then if you straighten it up, then I think, yeah, there you get it. Similarly, this is, I think, one of your hostel blocks, if I'm not mistaken. But so all this, so this rolling shutter correction is again completely based on this homography idea and so on that you have already learned. But except that now you can, right, escalate this challenge. Look at this case, right? This is the same thing, but then this is like some animation, right, which will tell you how these curves are getting straightened up. So if you watch this figure, right, you will see how right, I mean, eventually, okay, so these curves, okay, that are kind of right initially there. So for example, if you look at this guy, right, this is like curved, no? So as you keep going, you see that it's kind of straightening it up. So it's an optimization problem. Okay, this one is solved as an optimization problem where you try to maximize the number of vertical lines that you can expect to see, and all these assume some prior and so on. It's like an indoor. The same thing will not work. I mean, if actually everything was curved in the real world, you would go totally wrong, because you may think that everything should be straight, whereas if everything is curved in the world, then you're finished, right? So some assumptions are there. Okay, again, so these are a fairly difficult problem. So therefore, one has to make some assumptions to be able to see this through. Yeah, this is again another example about a geometrical. This is inside a train, and that is a building. So now this animation will tell you, right, how it kind of straightens up. Right? Can you feel that? So how things, especially the pole, if you see in that metro train, the middle one, I think, yeah, that may be the one, that will give you a good idea. And similarly, the building, I think you can probably look at this edge, and you will see how it straightens up. Okay, so this is again an extension of this homography idea, but extension to the case, right, when you have a much more complicated situation. This is how the poles and all will start to look like. I mean, so if you have, this is how a rolling shutter effect will cause a pole to look like. And then if you actually do the correction, right, this is how it will look like. This is how it will become. Similarly, some building here. These are examples too. And yeah, and I also wanted to show you the case. Now, on top of this, if you want to escalate the challenge further, you can think of rolling shutter plus blur. That's like again at another extreme. Okay, it's not only that you have a rolling shutter, but then the exposure time is so long that you are starting to incur blur now. Right? Blur actually depends upon your exposure time also. The longer your exposure time, then your motion is also going to be that much longer, and therefore you are likely to integrate points from, right, many scene. You are likely to integrate many scene points at a pixel. So in this case, right, look at this. So here is an image that you captured when you were still. And then when you're moving, okay, the blur maybe you may not be able to appreciate it so much, but there is, okay, believe me, RSMB, that's why it's called rolling shutter motion blur, okay. And then when you align the two, right, now when you align, you have to account for the rolling shutter motion, right. So what we normally do is we kind of forward warp this guy, right, so that it looks like the one that is already, because doing the inverse warping is actually harder. So go the forward way, right. Forward warp this so as to be able to make this look like that. And then, okay, let's see, right. So if this is your original reference and this is a distorted guy, then the original reference you try to, now you can see the loss in sharpness, can you, right, between the two. Okay, now you take the original reference, and if you compute these homographies and all, right, you compute, I wouldn't call them all as homographies. Typically you have to know what is the camera motion row wise, and for which of course you know that, right, there is also correspondingly a homography. And then now you see, so the reference guy has been kind of brought to the same blurring level as that of your distorted image, and also in terms of the geometric this one, right, there is a distortion, it will also match in terms of that. And now if you take a difference, that you will find where the objects are, where the actual changes have happened, because you cannot subtract these two directly, you will go totally wrong. These two, if you subtract, right, everything will show up as a change, when ideally some of these changes and all, right. So for example, this road has become like that is not a change, right. Nobody physically went and changed the road there, correct. So things like that, so which we can attribute to camera and not to the world. Okay, this is one example. And then another thing, this is a kind of a drone. So here I wanted to show, right, I keep on saying about the parallax effect, right, I keep telling. So here I'll show you the parallax effect. So look at this building, right, which is kind of relatively tall, right, compared to the ground. Okay, now on this, if you move, okay, this let's say the first image. Okay, this is suppose a second image, which is actually distorted. So when you actually align the first one, right, you will see that the building will move at a kind of a different pace. See, okay, can you see the building moving much more than the ground? Are you able to see that? Right? It's almost like somebody is taking the building and moving it around, right? So that is a parallax. That is parallax. Okay, so unless you translate, you won't get that. And when you translate, pixels closer to the camera will tend to move more. Okay, and then on this also you can do. So this is for a 3D scene. This is something that I was talking to yesterday, right? Homographies you cannot apply, if you have a 3D. But then if you can segment, this is called a layered homography, in the sense that you have different planes, and then you kind of split the scene into multiple layers, and then have a homography for each layer, and then you can do things. Again, this is all stuff to just be aware of. Okay, not that, right, we want to do all this in a course, but it's good to know that such things exist. Then stitching, of course, this example I showed you earlier itself. So this is something like this is what you're going to do, except that we don't have something like this in Chennai, right? So you'll have to live with whatever you can capture with your cell phone. Go around, hunt for deer or whatever, but they will move. So okay. Now here it is, right? So here is another thing. So rolling shutter rectification and if you had to stitch. So if you see here, right, there is also a rolling shutter effect. See this cage. See this one, right? Which is getting. So it's like saying you're actually moving with a camera. Now you have a rolling shutter camera, which means that the motion as you're going through, right? Not all rows are experiencing the same motion, and therefore, if you're taken with a regular camera, right, this guy would have looked exactly the same in this picture also. Okay, but now you see that some things are getting stretched and so on. That is all happening because of the rolling shutter effect, and therefore, right, what you need to do is now you need to also find out what motion happened, right, row wise, and then again stitch. So it's much more complex than what we saw. Right? What is your lab assignment is much more simpler. We are not assuming anything like that. But really, right, and anyway, you can, any of you is interested, you can go read these papers. Right? These are all some CVPR, some SC journal papers and so on. And then underwater, right? So this is called depth-aware stitching. Right? What does that mean? Depth-aware we say because especially right for underwater, it's more important. Because in underwater, one of the problems is you cannot be too far away from where you want to image. Typically, when you want to image the floor, of the ocean and all, right? So people have these remotely operated vehicles, what are called ROVs. So these ROVs, even our NIOT. Have you heard of NIOT? National Institute of Ocean Technology, which is right here, 3 kilometers from our campus. They have these ROVs that can go, way down, and they can actually map the ocean bed. But then what will happen is, because you have to take your own artificial source, let's say you are taking an optical source, and because it has to be artificial, right? The sunlight doesn't come. 20 meters, you don't see anything. So what happens is, so if you stay too far away, thinking that by that I can avoid my homography issues, right? Then what will happen? You won't see anything because the light will not reach at all. So you have to be really close in order to be able to see the surface properly. But when you are really close, you know that the ocean surface is not flat. It'll have all these undulations. There will be rocks. You see, right, formations like that. And therefore, when you move and you want to map the bed, you have to inevitably face this situation that you have to do a depth-aware kind of a stitching. Okay, and so all those things are again. Okay, these are all. So it's not simply restricted to surface scenes, right? Like outside surface scenes, by which I mean, what do you call on the surface of Earth. There's also things that are kind of happening underwater and so on. Where again some of these notions are valid. This is again another example that I had given you that day, right? And I'd shown you this image. Now, if you see, right, this is like okay. I mean, in this case also there is a motion, but here it's like so it's like saying that if you had a wave, right? Imagine that you had a water wave, and suppose right. I mean, I kept a flat thing like this, a paper on which I have something else written on it, and suppose I keep it on the bed. Imagine your swimming pool, right? Imagine that in the bottom of the swimming pool I keep this, and let's assume that the sunlight is enough to fall on this. So when you have still water, right, you will see this as it is. But then the moment the water begins to flow, it will start introducing what is called a skewing effect, okay? because the rays will start to right, bend depending upon the slope of the water, right? And then you get what is called a skewing effect. Now this is not exactly a homography, but then it turns out that it can be simplified in some manner, and you can actually arrive at a very, very elegant solution to remove that skew. So here it's almost like saying that every pixel will move, right, depending upon the slope of the water it saw at that time. But so you capture a bunch of frames, but you can actually eventually solve it as a kind of a de-skewing problem. But this is how it will look like. So you see, so if you freeze it, right, you will see something like that is what you will see. Okay, now again, right, there's some skew. So if you stop the video in between, you will see each of those frames. There will be a few frames, so that's why I'm not able to stop it that way. Okay, so all these are things, right, that go far ahead of, right, what we have learned. But this is only for those that work in that area and so on. Right? So for you, it's enough to know what we have said already in the class. Now let me now go back to. Okay, let me now go back to my to what I call a real aperture camera, to our next topic. Okay.